So we have this equation called logistic equation. So it's a differential equation that's kind of looks vaguely similar with Newton's law of cooling. And this is usually the modification of just instead of just saying e to the x where it goes unbounded, or even Newton's law of cooling, we have kind of like a slow start and some rapid increase in the middle, and then a slow finish if it's increasing or something like that. Yeah, I would call it that, but kind of. Sideways cubic has a vertical slope in the middle. I don't think this has a vertical slope and goes infinitely positive and negative. Here you have asymptotes. All right, so let's take a look at this problem. We have n denotes the number of supermarkets that use some computerized checkout system. And then here's a differential equation that we have. It is an autonomous differential equation. What does autonomous mean? So the dependent variables on the right-hand side, there's no independent variables that exist there. So that's what's called an autonomous differential equation. And then whenever we have an autonomous differential equation, back in chapter 2, I think we found a way to try to graph it. I think we were looking at slope fields and stuff. And then with an autonomous differential equation, we have what's called a phase portrait. And what we want to do is we want to essentially look for when the slopes are equal to 0, because that's when it levels off. And those are what's it called again when this is equal to 0? Yeah, it's equilibrium points. So at those points where there's an equilibrium, these graphs either go towards the equilibrium or go away from the equilibrium, or they could do both, depending on where you start. So let's take a look at this problem. Try to imagine what the phase portrait might look like. And what we want to do is we want to essentially set the right-hand side equal to 0, or set when the derivative is equal to 0. And that's equal to 0 when n is equal to 0, or n is equal to whatever you get when you solve for this. Is it 5,000 or 500 or 50,000 or something? 2,000. Okay, so you have a couple of equilibrium points at n is equal to 0. This is your n-axis. Remember, equilibrium, because this is autonomous, it's not dependent on the independent variable t. And so we can get the gist of how the graph looks like by just looking at the dependent axis, n. And then if we think about this as just a test where we're trying to see whether something's positive or negative, if we put an n value that's less than 0, for example, a negative, so that would make your negative number here a negative. And then you have something that's less than 0, this is negative, that would make this expression in the parentheses what? More than 1? So I guess I was looking for whether it's positive or negative. It's positive, right? So we have a negative times a positive, so this is a negative, so this is going to be a decreasing slope. So that means if you start off below 0, then you're going to continue to go down. we're no. All right, somewhere between 0 and 2000, we have a positive number going in for n now. And if it's less than 2000, like 1000 or like 1 or whatever, what's this thing in the parentheses going to be, positive or negative? So this is positive. So we're going to have an increasing. So 0 looks like it's unstable. You tend to stay away from 0 as you move from left to right. And let's see if 2000 is a stable equilibrium. And for that, we have to check a number that's going to be bigger than that, bigger than 2000. So you're still positive for the n, and then you have 1 minus this thing. If you put a number that's greater than 2000, this negative sign will dominate, right? So then we're going to have a negative. So this is going to give us a negative value. So it does look like we have a stable equilibrium at 2000. I think they call it semi-stable. All right, so that's the first part. By hand, sketch a solution curve. Oh, so by hand, I think we would imagine our solution curve to look something like this. We're at n of 0 is equal to 1, so we know that we're between 0 and 2000. And then, so the logistic growth here is that if you go off to negative infinity, this is going to approach 0. And then if you go to 2000, it's going to approach, as t gets larger, you're going to approach 2000. So your graph should look something like that. And then what we'll do is we'll solve for the differential equation and verify to make sure that that's actually accurate. So part B, they asked us to actually solve for this differential equation. They want us to figure out how many of these supermarkets are using the technology in 10 years or 10 years from the beginning. So how would we solve for this differential equation? It's separable, right? It's autonomous, so we can separate it. So we have dn over n 1 minus 0.0005n is equal to just dt. Yeah, so the right part seems like it's the easy part. How about the left side? How would you solve for that left side? How would you integrate that? We need to what? Oh, okay. So this is what you're saying? This is what it should be? All right. So this is partial fractions. So we're going to have 1 over 2000. And what's the antiderivative of this first one? Yeah, this thing. I think that's that's when you do. That's when you do one of these jobs and then solve for A and B. So I think somehow they got A to equal to 2,000 and B to equal to 1. So you guys should be able to do this because it's uh, it's Calc 2 when you had to find partial fractions. All right, so we're here now. We have the T plus C business, and then we need to somehow solve for N or something. So 2,000 times 0.0005. So it's negative ln 1 minus 0.005 n plus um, n equals t plus c. And put this into one logarithm. 1, 2, 3 zeros. So now we can take the e of both sides. And this is where you got the plus c business, so you can just have it as a coefficient. E to the t. And suppose we can pause here and try to solve for the constant, right? So I think t is equal to 0, n is equal to 1. So it's 1 over 1 minus 0.0005 times 1 is equal to a times e to the 0. So a is going to equal to this. Can that be written any nicer? Is that suppose we can just plug it in the calculator and figure that out. So what is this equal to? 1 divided by 0.999. We got to concur. Let's not get into the Taylor stuff. So let's just, what are we doing here? Are we good? All right. So what are we doing here? Are we good? Everybody else except for you guys who seem to be good. We could. I'm asking other people what they think. What do you guys think? Solve for n. So wait, is this a good number for a? All right. So we have n over 1 minus 0.0005n is equal to 1.0005 e to the t. I suppose how much did we round the a to? Say it again, Erica. 2,000 over 999. All right, well, that looks nicer. So one way to solve for n, I don't know if you guys remember this, but back in Algebra 1, I remember teaching Algebra 1 and having to solve for n like this in a weird position, weird way. There's two n's over here, so you have to multiply things to both sides and then bring things over. It's kind of like some similar moves that we had to do in when we're solving for your derivative when you guys were doing, what's that called? Implicit differentiation. So we can multiply both sides by this expression, the denominator, or cross multiply, or whatever you want to call it. Yeah, and then we'll just figure out where the n's are and then bring it all over to one side. So I have an n that involves this expression, and I have this n over here. So I'm going to distribute this first. Okay, so I have three terms. Two of the terms have an n, this one doesn't, so I'll bring all the terms with an n onto one side. I missed an e to the t here. And then you can factor out an n and then divide both sides by what you factored out. So you factored out an n, we have a 1, and then you have this other stuff. Now, we can do all kinds of other arithmetic stuff that you can just punch in your calculator or put in a computer and figure out what those numbers are, but this is the general idea, and this is what you need to be able to do. So at this point, do we have any questions? Okay. So now we get to put in t is equal to 10. So just plug it in, see what you get. Or you can just wait for your classmates to do it, right? We could. Say it again. Let's check out some numbers and let's see if it's reasonable. Is that reasonable? It's between 0 and 1,000 and 2,000, so that makes sense. Should equal to 1, right? Because that's what, yeah. Well, they didn't say years, they just say t is equal to 10. No units. So, anybody else get something different? All right, let's try to graph it. So I have to use x's and y's. We have the first one is a 2,000 divided by 1999 e to the t power to the x. One plus yeah. Somebody suggested that we take this to the negative first power. Went over 1999. Yeah, that was also suggested. Here's one. It looks like the exponential function, but let's shrink it. So this is t is equal to 10, and then your y or your vertical axis is 1833. Okay. This picture isn't going to fit. So that's kind of like what we sort of envisioned the graph to be based on our face portrait. And we know that it's going to, if it's coming between between the n values of 0 and 2,000, we know it's going to be increasing from left to right. And it tops off at 2,000. And so that's the graph. It's just too weird to put in our notes. I don't think it's going to fit anywhere. We're out of space. Oh well. Any questions aside from everything? Yeah. Nonlinear modeling. So in this nonlinear modeling, we're looking at these other types of differential equations that are not linear, and we're trying to model. Yeah, so this is a partial fractions kind of a deal. All right, let's do another example. The other example, I had two more examples that I was thinking about doing, but we're not going to have time to do both of them. The other one is this equation, which is fairly similar, I think. So maybe the other one is a little bit, so the other one is, I think this is a probably a good one to do. So this is number 17 in your textbook. So this one has was one of the problems that you guys did in section 1.3, 1.6, 1 point something, the buoyancy, yeah. And so this takes that and then actually tries to solve for it. Because remember back then you were just supposed to find the differential equation. So now that we know how to deal with first order differential equations, we should be able to solve for this. All right, let's read it out loud. Determine the differential equation for the velocity v of t for the mass m sinking in the water that imparts a resistance proportional to the square of the instantaneous velocity. So we have something already here, proportional to the square of the instantaneous velocity, and also exerts an upward buoyant force whose magnitude is given by Archimedes' principle. So I think if we think back, Archimedes' principle says something about the volume of the water or something like that. So we'll take a look at that, and then assume the positive direction is downward. Let B V be the volume of the water, rho is the weight density of the water, and then we have the gravitational acceleration. Well, let's see if we can break this apart. So the resistance, so the force that we're looking at has something to do with the square, the proportional to the instantaneous velocity. So F is proportional. What do you do proportional? So constant times the square of the instantaneous velocity. So that's one force that they're talking about. This is the resistance. And then I don't know. Force. Well, so the Archimedes principle says that your force, upward buoyant force, whose magnitude is given by the principle, is equal to the weight displaced. Um, so we'll make these negative. We can make it negative now, but I was going to make it negative later. So Archimedes principle is this so the buoyancy. So the density of the water. So this is the weight of water displaced. Okay. So that's rho times v. So the force, mass times acceleration, is the sum of the forces, including the acceleration is the gravity, mg, and then we add on these other forces, which contribute negatively because of the gravity. I mean, if this is negative also, but so minus Fr minus Fa, so mg minus kv squared minus rho v. We have what the force is equal to. Yeah, so we're looking for the velocity. Yeah. So it's a weight. So we want to turn the A into the dx or dv dt because acceleration is the derivative of the velocity. And we can divide out the m. So G, K, M, rho, capital V are all constants. Should we make this capital V look different? So capital V stands for the volume, and that's not the velocity. Okay? So this is our differential equation. What kind of differential equation is this? This is a separable differential equation, right? So what are the two variables that we're looking at? The two variables are little v and little t, and capital V is not a variable, it's constant. So when we try to solve for this, it looks like everything is going to have to go on the v side. All right, so we got a bunch of other constants here that's kind of look like it's going to make things a little messy. So let's see what we can do to try to simplify our integral that we're going to have to eventually integrate. So let's spend a little bit of time making this integral look nice for us. Let's see. We can put it all under one denominator first. Okay. So how do we want to do this? Okay, so why don't we just try to do it my way first? So this is the variable that we're looking at. Everything else is a constant. So why don't I try to combine g minus rho v over m together first? Okay. So I can also possibly think about multiplying by m over k on the top and the bottom so that v can be by itself. That look like an okay move? So if we do that, I have m over k dv over, so I have m over k g minus rho capital V over m and minus v squared. Right? Is that okay so far? Now, this whole big mess over here is just a constant. Yeah. Or A or something. Um, And we could do this a bunch of different ways, I guess. So if we take this whole expression over here and call it, say, maybe alpha, we can even attempt to put it together if you want, but I don't know. M over K G minus rho V over M. Better yet, maybe if we could call it alpha squared, because if we call this whole thing alpha squared, then we have a squared minus v squared, which is a nicer thing to deal with. And since it's just a constant anyways, it doesn't matter whether you look at it as being squared or square root or whatever. So now, let's keep this in mind. And now let's take a look at this as m over k dv over alpha squared minus v squared equals dt. Okay? So now there's a couple ways to deal with this. One is to split this up and then do partial fractions. Any other ways to deal with this? I don't know if we ever did hyperbolic functions. But if we look it up, we could probably find it, yeah? So what was here again? D, B, V. Oh, this is V. All right, that looks like it's a good good integral to work with. Got m over k plus 1 over 2 alpha ln v plus a alpha v minus alpha. Okay, so that's the left-hand side equals t plus c. Suppose we should bring everything over to the right-hand side. All the constants, that is. So v plus alpha, v minus alpha is equal to, now these are all going to do the reciprocal thing. So 2k alpha over m times t plus 2k alpha, those are all constants, right? So they kind of merge in with the other constant. So we have to try to solve for v. So we have e to this thing. So v plus alpha, v minus alpha is equal to e to the 2k alpha over m t, and then we can put the a in the front. Yeah, is there an initial condition here? No. Okay. C. Okay. All right. So let's solve for V like we did last time. We have V plus alpha is equal to, should we temporarily call this thing something? Like capital B? So that would be capital B times V minus alpha. And then we distribute B, V, alpha, B. So we find the ones with the V, bring that to one side. And then have the ones with the alpha, bring that to the other side. So V is equal to alpha minus alpha B divided by 1 minus B. All right, so we get to put in all the other stuff. We need to put in the stuff for alpha and the stuff for B. So we could factor out an alpha here just to, I don't know, where? What happened? So this one? Yeah? All right, just put alpha in. You guys have a test on Tuesday. You guys have, yeah, yeah, everything from the beginning up until chapter 3. Yeah, 3.2. No, 3.3. Why not? So you guys have to practice. Practice. I don't know yet. Um, it's more computational and more like on the computer kind of thing. So I'm not sure. I probably not, but I'm still not sure. If I can find a way to test more of the theory than the actual doing, then I might come up with it. No. Yeah. Is the rubric out yet? The rubric's not out? Ah, okay. Um, why don't you wait till tonight, and then I'll try to get the rubric done by then. Wait, yeah, and then it got postponed to Wednesday. Yeah, till Wednesday because Monday's a holiday. Yeah, 8.5 by 11, whatever you want. Yeah, yes. No magnifying glasses. Red, blue. Have you seen that before? No, no. Use a different color ink. Oh, I'd be curious to see that. 8.5 by 11. In WebAssign, you can ask for a request, so do it there. Well, I try to answer it right away, and then I'll